Imagine taking the most powerful racing engine in the world, setting it bare on the asphalt, and hitting the gas. It doesn't go anywhere. It just vibrates violently, smokes, and eventually tears itself apart. Large language models possess that same explosive, raw cognitive power, but without a structure to channel it, they are isolated, smart, but disconnected from any real environment. This chart shows AI success rates based on task complexity. There's high success on the left for simple chat questions, but moving right to autonomous, multi-step tasks, the line drops off a cliff, failing 70 to 95% of the time. Reliability is a product of the environment we build around that intelligence. When engineers see these failure rates, the solution is to shift the focus from the model itself to the system that surrounds it. Making AI reliable for real work is a system design challenge. In the industry, this is called harness engineering. So let's step into the garage. Our first priority is taking all that raw intelligence and forcing it to move in a straight, intended line. We start with global rules and conventions. Think of these as the chassis and the steering column. They are strict, rigid guidelines that force unpredictable text generation to conform to a predictable format. But an engine spinning inside a rigid frame still can't grip the road. We need a way to translate that power into physical movement. These tools act like the transmission and tires. We call them skills, using a standard called MCP, which is essentially a universal connector. It gives the AI the actual capability to execute actions, like writing to a file or querying a database. By wrapping the model in these rules and skills, the AI transforms. It goes from a passive chatbot waiting for a prompt into an active participant that can navigate a digital environment. Of course, once a vehicle can move on its own, speed becomes a liability. If it enters a corner too fast, it needs automated control to avoid a crash. This is where security hooks come in. They are the AI's brake system. These are hard-coded, deterministic barriers. If the AI tries to delete an important file or execute a destructive command, the hooks intercept the action and halt the system immediately. High-performance vehicles also rely on constant telemetry, reading real-time data to tweak performance on the fly, without ever stopping the car. For an AI, these are feedback sensors. They let the agent read its own error logs, recognize syntax mistakes, and correct its own trajectory before a human user ever sees a failure. Unchecked autonomy is dangerous, but when that powerful engine is wrapped in heavy-duty security hooks and sensitive feedback sensors, it can operate safely and scale indefinitely. Now, with the chassis, tires, brakes, and telemetry in place, that same raw power launches cleanly off the starting line. The workflows execute perfectly. The system holds together. Right now, there is a clear divide in the tech industry. Casual users act like frustrated mechanics. They run a prompt, watch it fail, and abandon the project, assuming they just have to wait for a newer, smarter model. But the top 2% of engineers see it differently. They know current models are already highly intelligent. They focus entirely on extracting that intelligence. This equation shows their mindset. An AI agent equals the model plus the harness. This shift changes a developer's day-to-day work. We're moving from writing every line of code ourselves to managing fleets of intelligent systems. AI is not a magic oracle that understands intent. It is an engine. And the individuals and organizations who learn to build the best race cars will be the ones who win the track.